Hi, welcome to video 2 on Unit 1. Today we're going to talk about evaluating limits. We're going to talk about what it means to be a left-hand versus a right-hand limit, if they exist, how to simplify some situations so we can find limits, and then using graphs to find limits. So let's take a look. In example 1, the first thing you want to do, if your graph is just a very basic function, like a linear function, a quadratic function, you're not going to have, your graph is going to be continuous. There's going to be no breaks. That's what you're always hoping happens when you're doing limits. It's the easiest. And so the first thing we do is just plug in the value and see if we can evaluate it. So I'm going to plug in 1 for x and see if I can get out an actual value. Yeah, I get out 3. That's what my function approaches. If I actually looked at the graph, I'd end up with something like this. Here's 1, and you can tell the graph approaches the same thing on the left and the right. Okay, in example 2, if I tried plugging in 1, let's see what I get. 1 plus 1 minus 2, 1 minus 1, I get 0 over 0. Now, I talked about this yesterday. When you have 0 over 0, and we're going to see this in a second, a lot of times there's something that you can do to simplify this function right here so that you can actually evaluate what the limit is. So let's take a look at what happens. We're actually going to factor the top to make this simple. So notice I still have the limit notation because I haven't plugged anything in yet. The top factors into x plus 2, x minus 1. If you forget how to factor, you may want to Google just some simple quadratic factoring techniques and just go through some examples because you should know how to do that. You've been doing that since Algebra 1. Okay, let's see. Whoa, check this out. Do you see how this number 1 here, if I plugged 1 in, I get 0 over 0. That's what's causing this. And this right here should be in the future a tip off for you that there's probably this scenario where you can find the factor on the top and the bottom and actually get them to cancel. So this was like a big red flag that I could do this. I just had to figure out how. Okay, so then when I cancel it out, what I notice is this just simplifies to the limit as x approaches 1 of x plus 2, which, well, that I can certainly plug in. I get 3. It actually ends up reducing to the same problem we did in example 1. Okay, let's take a look at another example. In example 3, again, the first thing that I should do is plug in 9. But if I do plug in 9, I get 9 minus 9, which is 0 on top, and square root of 9 minus 3, which is 3 minus 3, 0 on bottom. So again, I get that 0 over 0 situation, which means there's probably something I can do to simplify. Okay, factoring may not seem like the most obvious way to solve this. You actually can use it, but I'll do it as a separate example. The way that we're going to work with this is, do you see this bottom here? This bottom has a square root and is being subtracted by 3. In pre-calculus and algebra 2, when you wanted something like that to simplify, you usually multiplied that by its conjugate. So what is a conjugate? Well, if you have a plus b, if you're adding two things, the conjugate of that is a minus b. And we use conjugates because when we multiply them, the middle terms are going to drop out. Like my middle terms here are negative ab and positive ab and then minus b squared. So these things cancel. And oftentimes we're going to want that to happen for a particular reason. I'm going to show you that in just a second. Okay, so if I want to find the conjugate of the denominator, which is square root of x plus 3, and I'm going to multiply the top and bottom of my fraction by that. Again, you use this technique in pre-calculus and in algebra 1 and probably algebra 2 to simplify the denominator. So again, I'm going to take the conjugate of this radical part, which is root x plus 3, and I'm going to multiply top and bottom by that. Okay, so why? Well, take a look at what happens. I'm actually going to start with the bottom. So when I multiply these two, they are technically binomials, meaning they have two terms. So if you could imagine there's parentheses around them. If I multiply them out, I get root x times root x, which is x. The middle terms are going to drop. I showed you that here. And then negative 3 times 3 is negative 9. Now, I don't like the looks of that. Minus 9. Okay. So now I could multiply the top out if I wanted to, again, treating it like this, but I don't want to. In fact, I am going to give you the suggestion that whenever you do this process of multiplying by the conjugates, that you always multiply out the parts that are actual conjugates, but these guys always leave them factored separate. And I think you can see why in just a moment. Check this out. We found that 0 that we can cancel. Again, remember, if I plugged in 9, I get 0 here and 0 here. That was the whole 0 over 0 business from the beginning that we could cancel. So now, notice I still have my limit. I've got root x plus 3. Now I can plug in my 9, and I end up with 6. Okay? All right, now there's actually a way to factor this. The top of this guy factors. If you recall, when you had difference of squares, these two guys factored into a plus b and a minus b, or some of you might have seen this as like an actual example would be x squared minus 25 factors into x plus 5 and x minus 5. And that top that we have, x minus 9, doesn't look like it would factor because x isn't a perfect square, but I could separate it. I can figure out what these two positions need to be by taking the square root of both of those. So if I take the square root of x, I get the square root of x. And if I take the square root of 9, I get 3. So I get x root x plus 3 and root x minus 3. It actually does factor into that, which in this case would be helpful. Take a look at it. So I can factor, and this is a way you're welcome to use. So that would mean I'd still have the limit as x approaches 9. My top would now factor into root x plus 3 and root x minus 3, which, aha, now we can see why that factoring would have been helpful. Bam, bam. And then you end up with the limit as x approaches 9 of root x plus 3, which obviously from over here we saw was 6. So that's just two different ways you can do that. Okay, in example 4, immediately I should plug in my value and I get 1 over 0. Now, this is different. This is not 0 over 0. 0 over 0 would let us know that there's something we can do to simplify, but whenever you end up with some number over 0, you can't cancel the 0 out. So that means that there's technically a vertical asymptote, and that means that my graph looks something like this with that little vertical asymptote here. And remember, the limit means is there a value when I get closer to 0 on both sides that my function approaches? Well, clearly this guy's going down forever. This is going up forever. They're definitely not flattening out to some y value. So there's no way that you're going to have a flat y value limit here. So we just say D and E, which means this limit does not exist. Those are the ones you hope to get. All right, in example 5, again, if I plugged in 2, which I should do, in this one I get 0 over 0, always plug it in. You never know. Sometimes you're going to get problems where it could factor, but you don't even need to factor because you plug it in and you get like, 1/7 or something, and you're done. And this one I can tell you right now, you're going to get a 0 over 0. So I'm just going to go right into the factoring. So in this one, I have the limit as x approaches 2. I can factor the top. I get 2x and x, and I get 2 and 1 and minus. Okay. On the bottom, I end up with an x minus 2, a 5x here, and a plus 3. Again, if you need review with factoring, you're going to need to go online and find some places to review quadratic factoring. It's not hard, and there are tons of resources. So take your time and find that if you need to. Okay, so check out what happens again. This 2, which would make the 0 over 0, cancels. That's kind of our whole point. We can reduce this down to 2x minus 1 over 5x plus 3. Now I can actually plug in 2, which gives me 3 over 13 as my limit. All right, in example 6, they asked, this is the first time we've actually seen sided limits this year. You should have seen it last year. Remember that this means as x approaches 1 from the left. This means as x approaches 1 from the right, from the positive side, from the negative side. And this again is just that general one. So in this function here, it's a piecewise function. We have a value when x is less than 1. We have it when it's equal to 1 and when it's greater than 1. If I want to know when it's coming from the left, I want to know when it's things that are smaller than 1, which means I'm going to look at this guy. So when I plug in a 1 here, that's my limit as I'm approaching from the left. So if I plug in a 1, I get 3 minus 1 or 2. So that side approaches 2. For the right side, I want things that are bigger than 1, which would be this guy, because see, it's x is greater than 1. It's not equal to 1, but that's okay. I just want to know as it gets closer from numbers that are bigger. So when I plug in a 1 there, I get 1 squared plus 1, which is 2. So then if I want to know if there's a limit as x approaches 1 in general, remember, the definition said that you'd approach the same thing on either side. Well, do you approach the same thing on either side? Absolutely. So if these two things agree, then you know you're going to have a limit as it approaches 1. Now, this graph actually ends up looking something like this. At 1, I'm 4, a closed dot. I think on this side I approach 2, and then if I plug in some other points, I get like something like this. I think this side's quadratic. So notice you do approach the same thing on either side, even though this point is at something different. I didn't ask if when it was equal to 1, I asked as it approached 1. All right, so our last example has a graph already given, and we're going to look at some of the values from that. I'm going to have to scroll back and forth a little bit. This first one asks me to talk about as x approaches -4. So we're looking here. Okay, the first one asks for -4 from the left. Let's look. As we travel from the left, we approach this y value, which is 0. As I approach -4 from the right, from the positive side, I'm approaching 8. So is there a limit in general? No, it does not exist because I'm not approaching the same thing. This is asking what is my actual value when I plug in -4? Well, as long as you have a closed dot, you have a value. When I plug in -4, I'm actually 0. Okay, let's look at 2. This asks us to discuss what's happening at 2. So from the left or from the negative side as I'm approaching, it looks like a y value of +2. From the right side or the positive side as I come along, I'm also headed towards 2, which means, yes, in general, I'm approaching 2. Now, what is my actual value at 2? Notice this is an open circle. That's not a value, but I do, bam, have a dot on 2. It's just at -3. All right, and my last one asks me to look at what happens at 6. So let's scroll down here. Same pattern. So I'm going to look at left, right, 6, and then f of 6. So from the left, if I'm following my graph from the negative side, I'm approaching 2. On the positive side, or from the right, I'm approaching 8, which means in general, do I have a value as I approach 6? No, because these disagree. Now, do I have an actual value at 6? Could I plug in 6 from Algebra 1? Yes. If you go over to your graph at 6, do you have a closed dot? Sure. It's at 5. So you're going to get some practice looking at graphs. You're going to get some practice factoring, using conjugates, and sometimes you're going to have limits that don't exist. Remember, if you end up with, 5 over 0 or -3 over 0, anything over 0, that's not 0 over 0, then your limit just doesn't exist. When you have the 0 over 0 situation, there's something you can do to simplify, and you're going to have to work to find that. All right, good luck with the problem sets.